First of all, let me start by thanking the organizers for inviting me to give a talk. Today I'll talk about string perturbation theory of Klebanov-Strassler with the hope that this will be useful for us to understand SUSY breaking back in string theory in general. And if you have any questions or comments, or if some points are not clear, just interrupt me anytime. I think usually it is much better to have some interactive talk. So before I go into the main part of the talk, let me first give you the high-level overview of the talk. And I think we all agree that lack of tools to really understand non-supersymmetric string backgrounds is one of the main challenges to really understand the boundary, the sharp boundary between the landscape and the swampland. So we need to build more tools, we need more general tools. In this talk, what I'll explain to you is how to use string field theory to get some controlled approximation scheme to study KPV like SUSY breaking scenario. And I'll be honest, one unfortunate thing that happened in my work is that even the computation to just reproduce the KPV result, which was a well-known result in the supergravity literature, was rather technical and involved. So you might find that, okay, even though it might be in principle possible to really do computations in string field theory, it is rather hopeless to really go to high order in alpha prime. Although that is a fair worry, I really believe that it might be possible to put string field theory on computer and then just press a button and to go to high orders to compute many impressive diagrams or terms in whatever actions that you want to have. So maybe the situation is not so bad. But anyhow, let me get to the main part. So this is the plan of the talk. First, I'll introduce the problem to you, and then I'll tell you why I think string field theory might be a good idea, and what is string field theory. And I'll tell you about how I'm going to approach the problem, and then I'll tell you how you can actually use string field theory to study anti-D3 SUSY breaking, and then I'll conclude. So, as I said, we need some tools, some general purpose tools that we can use to study non-supersymmetric string backgrounds. And the unfortunate situation is that although we like to do very impressive things, in the absence of a better option, we often take pseudo approximations. By that, what I mean is that we like to use some wall sheet descriptions or more non-perturbative descriptions to study non-SUSY backgrounds, but we don't really have those tools in many cases. We like pseudo approximations because it has some benefits, but it also has clear downsides. The benefits being that the computations are more straightforward, we know the rules of the game, but what I really worry about is that we might have reached the boundary where we have exhausted the benefits of pseudo approximations and the cons have become unignorable. In particular, the thing about supergravity approximation is that we do not really know how to compute alpha prime and G string corrections within supergravity unless you expect that some supersymmetric protection or some symmetry reasons are present so that you can actually guess what the answers should be. And alpha prime and G string corrections are input from string theory, not something that you can really compute within supergravity. Furthermore, it is not really clear how to compute genuine quantum gravity amplitudes in supergravity related to the previous point. And if you think about it, in a way, the whole point of doing string theory is because we want to understand quantum gravity. So in many ways, low energy supergravity is not really enough, and we need to find a way to go beyond it. I would say KPV, or anti-D3 SUSY breaking, is one of such examples where the lack of microscopic understanding is really hampering us. For example, we have an incomplete understanding of alpha prime corrected D-brane action, and that has been one of the main challenges to understand the KPV type SUSY breaking. I cited some papers here that try to understand alpha prime corrected D-brane action in the context of KPV. And then I want to highlight this very impressive paper that did a very impressive computation. So what this paper by Simon Schreier did was to take some the anti-D3 brain action with some known terms, with some known alpha prime corrections, and he tried to understand how the alpha prime corrections changed the story of KPV. Unfortunate thing is that he couldn't really arrive at a decisive conclusion because some alpha prime corrections were not known. And that actually exemplifies the importance of tools to compute some alpha prime corrections to the D-brane action, for example. And as I said earlier, due to the Raman-Roman fluxes, the conventional string perturbation theory breaks down. But a nice thing is that recently we have begun to realize that string field theory can provide you a framework to study Raman backgrounds. So, as you might have guessed, I'll try to explain how string field theory can help us study those backgrounds. We're going to talk about string field theory. Let's first briefly review the Klebanov-Strassler method and KPV. So the Klebanov-Strassler solution is a solution in low energy supergravity that aims to engineer a Randall syndrome-like solution to induce a huge IR redshifting, especially when you're gluing such a solution into a compact RBL. So you can think of the IR redshifting as something that is encoded in this warping factor e to the 2a. Typically, what you can do is to well, not typically. So to find such a solution, what you do is to first start with the deformed conifold, and then you turn on some fluxes, like Raman 3-form fluxes, and SNS 3-form fluxes. And then what you can do is to solve the Einstein's equation by including the back reaction, and then you'll find some the warping factor that will give you the some information about the IR redshift. But let's first talk about the deformed conifold, and then I'll also give you some more details about the deformed conifold because that will be useful for the later. So the deformed conifold is basically a cone over S cubed times S2. So IR, from the IR region to the UV region, you can imagine that there is a radial direction. In the case of the deformed conifold, what happens is that as you go to the tip of the throat, the S2 will shrink to the 0 size, but S3 will stay finite. A very nice thing about the deformed conifold is that you can embed the deformed conifold into C4 and write down the equation, and then you can explicitly compute the metric for the deformed conifold, which is given here. And let me explain a few symbols here. Tau is basically the radial direction from the tip. G5, G3, G4, you can think of them as some differential one forms on S cube, and G1 and G2 are one forms on S2. And epsilon is related to the size of S cube at the tip. And as you can see, when you're going to the tip where tau is equal to 0, you can see that the manifold described by G1 and G2, which is S2, will shrink to 0 size. On the other hand, the manifold described by G5, G3, G4 will stay finite as you go to the tip. K tau is some complicated function of tau, but it doesn't really do a funny thing at the tip. So as I told you, I'm going to turn on the fluxes on this manifold. And I'm going to choose a very particular choice of fluxes. I'm going to first turn on the Raman 3-form fluxes, m units of Raman 3-form fluxes on S cube, which basically look like this. And I'm going to turn on H3 on the dual cycle, such that the SUSY is preserved. Once I do that, as I told you, you can solve Einstein's equation to compute the back reaction and to compute the warping, and this is what you find. H tau is a very complicated function in the radial coordinate, and when you move far away from the tip, you can redefine the radial coordinate in R, and it basically looks like the usual Green's function plus some logarithmic running. When you go to the tip, On the other hand, what you find is that this h of tau will asymptote to a constant value that is proportional to some factors of GSM and epsilon. What this warping factor does for you at the tip is to basically replace the size of S cube with GSM, some factors of GSM. So before the warping, the size of S cube was basically a function of epsilon, but after including the warping, the size of S cube will be some power of GSM. So what it means is that as long as GSM is large, the size of the tip, size of S cube at the tip will be quite large. So the supergravity approximation is good as long as you maintain that G string M is really large and G string is small. And whenever you see GSM, you can basically think of GSM as some the typical length scale in this solution. And this is some comment that is not really important for us, but when you're thinking of gluing this kind of a Klebanov-Strassler solution to a compact labial, you can match some of the parameters into the parameters that you will get after doing the explicit moduli stabilization, and then indeed you will find that the Klebanov-Strassler throat will generate exponential hierarchy. But anyhow, this is the Klebanov-Strassler solution. Now, the reason why I'm interested in the Klebanov-Strassler solution is because it induces higher redshifting, and then you can place some SUSY breaking sources at the tip to break SUSY at low energy scale. And a well-studied example of this kind is the anti-D3 brain SUSY breaking by Katra, Pearson, Valinde, which we typically say as KPV. And KPV asked a very important question. So if you put an anti-D3 in a SUSY preserving vacuum, then it will break SUSY. And then in general, what we expect is that even if the SUSY breaking configuration is metastable, it won't be absolutely stable. It will decay back to some SUSY preserving configuration. Then the question that one should ask is that, okay, when is the metastability present? And if there is metastability, what is the decay time or the lifetime of that SUSY breaking minimum? Okay, so that is the configuration, that is the scenario that KPV studied. Roughly, there are two possible cases, but let me explain roughly what happens. So suppose that you place a stack of P anti-D3 brains at the tip of the throat. And at the tip of the throat, basically S2 shrinks to the zero size, so I can just focus on SQ. And suppose that I put the anti-3s at the south pole of SQ. What happens is that due to the Myers effect, the anti-D3s will puff up to NS5. And then, depending on some parameters, either NS5 can be stuck at a local minimum, which is a metastable minimum, or NS5 brain will decay into a set of D3 brains. And the parameter that determines the metastability in this context is P over M, where P is the number of anti-D3 and M is the quantum of the background Raman flux. And what KPV found is that when P over M is sufficiently small, meaning that the back reaction is sufficiently mild, there is a metastable minimum where NS5 brain can stay for some time. And what was also found is that when P over M is greater than some value, the metastability disappears and NS5 brain just decays into a stack of D3 brains. And the other point that I want to emphasize is that the location of the minimum is roughly scales like 1 over radius, maybe 1 over radius squared. And this is exactly what was found in KPV, assuming that some alpha prime corrections are not very important. And Well, the very important point is that eventually what we want is to glue the Klebanov-Strassler through to a compact Calabi-Yau and engineer some SUSY breaking sector there. You may think that, okay, in the Klebanov-Strassler case, you have some parametric control over P and M and G string, so that you don't really need to care about alpha prime corrections. But unfortunately, when you're trying to glue that KPV and the KS solution to a compact Calabi-Yau, we're not in a situation where we can just control all those parameters. Those parameters will be fixed by moduli stabilizations, and typically what we find is that it is not really possible to have arbitrarily small P over M and P over GSM square. So typically what you find is that it is not really clear whether or not you can ignore alpha prime corrections. So a very important thing that we need to do is to understand exactly when we can safely ignore alpha prime corrections, and if we cannot, how many corrections we need to compute, for example. So it is really important to extend the analysis of KPV to higher orders in alpha prime, or we can do more ambitious things if you have some capabilities by doing some non-productive analysis, although it is rather futuristic at this point. Good. So the problem itself is quite clear.
Excuse me, Manki, can I ask
Yes.
something? Yeah.
Yes.
So does that mean that in a holographic context, where I look at a non-compact Calabi-Yau, you would say that the calculation by KPV was under control?
I wouldn't exactly say that because of the following reasons. One, strictly speaking, so okay, KPV did two computations, right? One by using NS5 brane picture, one by using the S-dual action of the anti-D3. So the NS5 brane picture, I'm not sure whether or not this is a controlled calculation, that the wall volume action or the wall volume theory of NS5 is expected to be strongly coupled. And I don't really know how to do some calculations from first principle in the context of NS5 SUSY breaking. The other thing, the S-dual action of anti-D3, it might be more controlled, but one thing that I'm not really sure is whether or not, okay, I'll just say this way. The use of the anti-D3 action in the S-dual frame is well controlled when, strictly speaking, G string is much, much larger than 1. Of course, we kind of expect that the D3 brane action is S-dual invariant, but it is not clear how to really show that in the presence of the fluxes. So I think what we need to do is to either confirm the S-dual invariance of the D3 brane action in the presence of the fluxes, which is a likely outcome, or a better thing to do is to also come up with some direct approach where you can just compute everything without relying on any S-dual type argument. So
right, but so then you agree that officially the computation done was not under control, right?
Yeah, I think that was also noted in the original paper of
Exactly.
KPV. Yeah.
I just want to point out that if it's for more fino motivations, you can also look at a solution where you flip the NS flux with RR flux and vice versa. And then you actually are puffing a D5 brane and you can work with the usual D3 action. And I would say in that case, it's under control, but then the holographic dual is not understood. That's just a side remark.
Yeah, I agree. And also, yeah, that's a great point. Also, I think it might not be very easy to engineer such it might not be very easy to glue such an S-dual type Klebanov-Strassler into a compact Calabi-Yau. Yeah, but that's a great point.
Okay, thank you.
Yeah, so yeah. And actually that discussion was perfect because what I was about to say exactly that. So the reason why it has been rather difficult to understand KPV or alpha prime corrections to KPV is the following. A common approach that we use is to use the low energy supergravity action and DPI action for D3 and NS5. This is incomplete because our understanding of the D3 and NS5 brane action is incomplete. We don't know the full alpha prime corrected action. And at the same time, as I said, NS5 brane wall volume theory is strongly coupled, expected to be strongly coupled, so we don't really have a good theoretical control. And because we're breaking SUSY, we don't really have a chance of having some exact techniques available to study the KPV times scenario. And at the same time, we all know that string perturbation theory based on the RNS formulation breaks down. So this is the list of challenges, and I think we need to overcome those to really understand SUSY breaking. And so why do I think string field theory might be a good idea? Let's first talk about why it's been difficult to study the Raman backgrounds in the usual string perturbation theory based on RNS formalism. As we know, we don't really have any access to the Walsh CFT for the Raman backgrounds. And because of that, the best we can do is to probably start with the Walsh CFT for purely NSNS backgrounds, for example, some geometric backgrounds, and deform the Walsh CFT with Raman fluxes. In superstring perturbation theory, there is an unfortunate technical detail which is called picture number. And what you need to ensure is that when you're deforming the wall-sheet action, the picture numbers of the terms that are entering the wall-sheet action should always be 0, 0 picture. On the other hand, what a very unfortunate thing is that Raman vertex operators always have half-integral picture numbers. So there is not really a well-defined way to deform the wall-sheet action using the Raman vertex. And you can use some tricks. For example, the trick studied by Bernstein and May in late 90s to come up with some prescription to deform the wall-sheet action using Raman vertex operators, but they will inevitably induce some locality to your wall-sheet action. So this is basically the reason why it's been really hard to make sense of the Raman deformations in the RNS formulation. But if you think about it, it's not really the end of the story, because despite that we don't really know how to deform the wall-sheet action with the Raman fluxes, we still do know how to compute scattering amplitudes involving Raman states. So you might hope that maybe you can possibly compute the scattering amplitudes in the background field method to study some backgrounds like Raman backgrounds. So that's the philosophy that we're going to take. And let's try to formulate the foregraphed and amplitude in Raman backgrounds at string tree level to see where the usual string perturbation theory fails and how string field theory can help you. So here I'm drawing some tree level diagrams with foregraft and vertex operators. And because I'm doing the background field method, I'm inserting 2 Raman vertices, and then there are supposed to be more diagrams with more Raman vertex operators. And if the Raman fluxes are, for example, exactly marginal deformations, then this equation will be the end of it. This equation will give us the well-defined prescription to compute graviton scattering amplitudes in the Raman backgrounds. Unfortunately, what happens is that the Raman fluxes are not exactly marginal. They induce Weil anomaly. And when you have Weil anomaly, you need to shift the background. By shifting the background, what I mean is that you also need to include some back reactions in your diagram. And when you have a back reaction, the definition of the BRST operator also changes. Then the BRST quantization condition for the graviton vertex operator also changes. So you also need to include the shift of the graviton vertex operator. And then there are more high order terms induced by the Weil anomaly. And the second line, if you think about it, although you may try to compute on-shell amplitudes in the Raman backgrounds. In terms of the original Walsh CFT point of view, the second line is actually the off-shell amplitude in terms of the original Walsh CFT data. So, and at the same time, we don't really have a way to describe the off-shell amplitudes in the conventional string perturbation theory. And that's where even the background field method breaks down in the RNS formulation. But this is not a bad thing because string field theory is really the whole thing about string field theory is to give you an off-shell formulation. So what you realize is that, okay, maybe we can use string field theory to study the second line so that we can study the Raman backgrounds. And that's where string field theory comes in. So then let me tell you about what is string field theory. As I briefly alluded to, string field theory is an attempt to formulate string theory out of shell. The original hope of string field theory was to formulate non-perturbative string theory by giving a well-defined path-integral measure that is non-perturbative. Although, unfortunately, I think that hope has not been realized yet. As input, what you do when you're studying string field theory, you first start with a well-defined Walsh CFT describing some on-shell string backgrounds. And then you use that on-shell string background to compute all kinds of off-shell amplitudes and off-shell path integral. And that is the output of string field theory. And as I said, it is not really yet shown if string field theory is the right approach to formulate non-perturbative string theory, but at the very minimum, what we can do is to use string field theory to do background field method computation to study, for example, Raman backgrounds. So I'll tell you how you can construct string field theory, and let's take a very simple example, bosonic string theory, that has 26 bosons and the BC-GO system. In the usual string perturbation theory, what Polchinski tells us to do is to collect all the operators from the Go system and the meta CFT and construct some vertex operators. And then what you're supposed to do is to impose the BRST quantization condition, which will fix the momentum squared, for example. And T is the polarization for the tachyon field, and epsilon mu is the polarization for the metric, B field, and the dilaton. On the other hand, in string field theory, we're proceeding in a slightly different way. What we do is, again, to collect all the operators and vertex operators, but we're not imposing the BRST quantization condition. And we're treating T and epsilon mu as fields. And because we're not imposing the BRST condition, yes?
Yeah, could I ask just a quick general question about string field theory?
Yes.
Yeah, so in string perturbation theory, we often study things in light cone gauge. Life is simple and stuff. And that's also something you can do in space-time. And for any quantum field theory, you can take the light cone limit and it becomes like a light cone quantum mechanics. Is that something that can be done at the string field theory level as well? Like you get like a, light cone string quantum mechanics or something?
Yeah, actually, there were some attempts to do the light cone gauge in string field theory. In bosonic string field theory, that light cone gauge was rather successful, but there are some problems with light cone gauge. For example, if you want to study the background shift, I don't really know how to do the light cone gauge. And at the same time, if you're trying to do superstring field theory with the light cone gauge, what happens is that the technicality that I just told you, PCO, will always cause a problem at some interaction vertices, and they will cause some divergences, and then we don't really know how to properly deal with them.
Not very helpful for this. Okay, thanks.
Yeah. So usually supersymmetry makes our life easier, but in the context of string perturbation theory, supersymmetry makes our life more difficult. Anyhow, so Now that we have the string field, the goal is to construct string field reaction in the patentable measure, although I'm not going to talk about how you can construct the patentable measure here today. So as I told you, the on-shell condition for string fields or general string states are given by the BRST condition. And if you remember from usual field theory, the on-shell conditions are obtained by varying the kinetic time. So you can probably guess that this kind of a condition can be obtained by varying some kinetic time in this way. And that leads to the following guess for the kinetic action. And actually, that is the right form for the kinetic time for the string field. So we'll take this term as the definition for the kinetic term for string fields. Now, what we need to do is to construct interaction vertices. In string theory, we're in a rather special situation. If you think about how we are doing perturbation theory in usual QFT, what we often do is to start from the action and find a vacuum or find some settle point, and then we vary around the settle point, and we write down Feynman rules and compute amplitudes, right? But in string theory, we're not given the action, but we're given the amplitudes, so we're going backward. So what I'll do is to compute the amplitudes, isolate the contributions to the amplitude that are coming from the contact vertices, quote unquote, contact interactions, and then using contact interactions, I'll reconstruct the action. So let's start with the simplest case, the 3-point amplitude. So what we know is that 3-point amplitude only gets contributions from the cubic vertex. So what I'm going to do is to declare that the whole 3-point amplitude corresponds to the cubic vertex interaction in my string field reaction. And this is some complicated function of polarizations and string fields. And remember, psi describes all kinds of vertices. So although this expression looks compact, it actually contains information about infinitely many fields. And for the later use, what I'm going to define this kind of bracket. This bracket is basically given by this identification. So what I'm basically doing here is that I'm only inserting 2 points in the amplitude, and then I'm treating one insertion as a generic state. And then I'll call this the string bracket psi square, which is basically a state. And this will be useful for the later stages. And now I can move on to the next point, the 4-point interaction. The idea is the same. I'm going to first compute some amplitudes, and then I'm going to exclude the contributions that are coming from, for example, joining the cubic vertices by a propagator. Declare that the rest of the time will give me the 4-point contact interaction. Okay, so I'll do this the following way. I'm inserting 4 string fields in the tree-level diagram, and then I can use SL2C to fix the location of the tree of the vertices, 3 vertices. And I can use the location of the one vertex that can move around as a modulus. And when I am at a generic point in the moduli space, roughly you can think of the Riemann surface with 4 punctures as this. So the intuition is that this diagram basically looks like some contact 4-point interaction. And similarly, what I can do is to bring the vertex that can move around to one of the vertices that is fixed. For example, if I bring the z to 0, what happens is that the Riemann surface will degenerate into this form where basically it looks like you're gluing 2 pens along a neck. And this basically looks like a diagram that is constructed by joining the 2 cubic vertices with a propagator. And that's the right intuition to have. And as I told you, I'm going to exclude this contribution to the from the amplitude to define 4-point contact interaction. And this is what I do. Basically, so when you're computing string amplitudes, you first compute CFT correlate and then you integrate over moduli, right? And then when I'm doing the moduli integral, I'm going to exclude all the contributions that basically look like joining two cubic interactions using a propagate time. And I'll, as I said, I'll declare that as 4-point contact interaction. And that will be a term in my string field reaction. You might think that, okay, there are infinitely many choices to exclude some rules, and what are those degrees of freedom? What was understood in the string field theory literature is that basically different choices of those disks or local coordinates basically correspond to the field redefinitions. So as long as we care about some uncontrolled quantities like background solutions and some spectrum in some backgrounds, you can just choose the local coordinates that are simplest for your purposes. And that is what I'll do. Good. And then similarly, I can leave one of the insertions as a generic insertion and then define a state. Once you have done that, now you know how to generalize this to arbitrary insertions with arbitrary Riemann surfaces, and then you can construct string field theory reaction, which is given by here. And then you can vary the string field theory reaction to also write down equations of motion, and you can use it to find a new background and find some quantized states, etc., etc. This is a statement for experts. This string field reaction satisfies the BV master equation. And what it means is that the pattern called the string field is basically well defined. And as you can see, what we're doing is rather somewhat quite not very elegant in that we're just, in a way, expanding some action in linearized fields. So what it means is that, in essence, a string field theory action contains infinitely many terms for infinitely many fields. So we don't really have a good organization principle for the terms in string field theory action. So at best, what we can do with string field theory is to do some perturbative computations unless we have a better organization principle to write down the string field theory action in a more compact term. So,
Manki, yes.
yeah.
So if I understand correctly, here you are taking your Feynman diagrams, and from that you are reconstructing the action.
Exactly.
Is it clear whether there is a unique way of doing this, or whether you are assuming how the Feynman diagram should look like?
There are infinitely many different choices, which are basically given by the choices that are related to how I'm defining those regions that are excluded from the modular integral. So there are infinitely many different ways to represent the contributions from the Feynman diagrams. But what you can show is that those different choices are basically correspond to field redefinitions.
So then at the end of the day, what you can show is that whatever prescription you take, physically they are all the same, no?
Yeah, exactly.
Okay, thank you.
Good. Any other question or comment? Good. Yeah, so as I mentioned, we were only able to do perturbative calculations at best unless we have a better organization principle. So we need to choose a problem very carefully, such that we can do some reasonable perturbative expansion. Otherwise, we don't really know how to solve things with string field theory. So what am I going to do with string field theory to study KPV? As I told you, as I emphasized many times, string field theory action is really poorly understood. And we know how to do perturbative computations only. The immediate worry that you might have is that typically to ensure that your solution is well controlled in the context of KS solution, you take a lemma where the number of flux quantum goes to infinity. And at the same time, wrong flux is quantized. So you might think that, okay, how do you even do productive computations when the flux quantum is gigantic? That's the worry that you can have. And at the same time, although I didn't explicitly say, to formulate string field theory, what you need is a well-defined Walsh CFT. And basically what that means is that you need some well-defined string background. And because you want to do some productive computation, the string background that you have access to should be closely connected to the background that you want to study after the deformation. And both of these are not really obvious at this stage. And so the challenge is to really find the good access point so that you can construct string field theory action and then make sense whether or not you can treat the gigantic flux quantum as some perturbation. So to do this, let us go back to the metric that we found for the Klebanov-Strassler solution. What you may realize is that there is an analog of the near horizon limit in the Klebanov-Strassler solution, which I'll call the near tip limit. Basically, what I want to emphasize is that when you're approaching the tip, which is given by tau is equal to 0, the space-time metric basically goes back to the usual Calabi-Yau compactification metric with some rescaling going. So this should give you a hint that maybe in the near tip limit, you might be able to do some computations with string field theory, because let's first forget about the Raman fluxes. If your space-time geometry basically looks like the Calabi-Yau metric, then you know that you can use the Walsh CFT for the Calabi-Yaus, and the Walsh CFT for strings probing Calabi-Yau is formally very well understood, and you can construct the string field reaction around the background. So this is a great situation. So if we can really establish that even the large flux quanta can be treated perturbatively, then what you can do is to start from this background, which is the Calabi-Yau compactification with some rescaled metric, and then we can deform the background by turning on flux quantum, order by order in some perturbative parameter. So I'll show you how you can show that how you can manage to massage the Raman fluxes into the form that actually shows that, okay, you can do some perturbation theory. But before starting that, I need to make a few comments. As I said, the Calabi-Yau CFT is formally well understood because of the extended SUSY. For example, we understand the chiral ring very well, and we also understand the index or the characters really well. But unfortunately, we don't really know enough about Calabi-Yau CFT to do the computations that, for example, constructing off-shell amplitudes. What it means is that we need some approximation scheme to really do some explicit computations. An obvious choice that you can make is to do large radius approximation at the tip, for example, because at the tip, the metric of the Klebanov-Strassler throw goes back to the Calabi-Yau metric. But if you think about it, at the tip, S2 shrinks to the 0 size, so you cannot really do a naive large radius approximation exactly at the tip, because some space-time dimension shrink to the 0 size. So what I'll do is the following. Instead of just taking the large radius expansion at the tip, I'll take a local coordinate chart that is separated slightly away from the tip. And then I'll take the limit where the radius of the S cube goes to infinity, and then I'll also take the distance between the local coordinate, the radial coordinate tau, and the tip to 0, such that the ratio between them is fixed. So basically what I'm doing is that I'm doing the computation slightly away from the tip, so that the size of S2 stays finite, rather large, depending on the value of the rate R you choose, so that you can do some large radius approximation. And then what you find is that in such a local coordinate or the coordinate chart in the Calabi-Yau, you can expand your Calabi-Yau metric. And then basically the Calabi-Yau metric looks like the flat space metric, implying that your large radius approximation is well defined. So using this double scaling limit, now then I'll study the Klebanov-Strassler electrode near the tip. And so what I'll do is the following. I'll write down the quantized free-form fluxes, F3, with G string factor, because when you're writing the vertex operator for the Raman fluxes in string perturbation theory, you should also add G string factor. And then I'm going to rewrite the flux in terms of the near-tip coordinate. And once you rewrite everything in terms of the near-tip coordinate, what you find is that the Raman flux quantum scales like 1/4 radius of S cubed. So what it means is that as long as you have some large radius where G string M is large, you can basically...
Manki, can I ask a question? So
Yes.
what is the justification for this double scaling limit? Is there an argument to say that this particular region is the most relevant one for your computation?
Yes, exactly. So the double scaling limit is engineered so that the computations, I can do computations in the chart that is really close to the tip, but not exactly at the tip, so that I can do some reasonable computations in the chart and then send the limit to study what is happening at the tip. And because we're going to put anti-D3 at the tip, this is a good target.
Yeah, but this requires some quantitative explanation, right? Because there must be an estimate of which region contribute most to the question of stability, and then to show that the double scaling limit exactly proves that region. So this is a quantitative question.
Yeah. Because the instability is the most sensitive to the IR region, and then I'm proving the IR region using the double scaling limit.
I agree, but the question is that in which IR limit? Because you said that the large volume limit doesn't work. And so there are a variety of different ways to take IR. So why this particular limit is relevant is the question.
Yes. So maybe one thing I can say, please let me know if I'm not fully answering your question, is that the anti-D3 branes will be attracted to the tip. And then the dependence on the radial or the ratio that I'm defining to be R, for example, will eventually drop out as long as you ensure that the anti-D3 branes will fall down to the tip of the drone. So the double scaling limit that I'm engineering will give you a tool that allows you to compute the quantities that are not really dependent on the R. For example, if your answer depends on R, then you don't really know what you're doing, but eventually all those quantities that depend on R will be washed out because the anti-D3s will be attracted to the tip. And for example, the question that we really care about is not how the anti-D3 branes move along the radial direction, but how the anti-D3s will pop up. And that is where the instability really comes in. And that question is really sensitive to the ratio that I'm taking for R.
Okay, I think it's going to be a long conversation, so probably we should do it some other.
Yeah.
But I did want to see that the correction to this double scaling limit is indeed suppressed. And so this is a quantitative question.
Oh, yeah. Actually, you can do the calculations and then you see that all those things drop out just because the quantities that do depend on the ratio or how I'm taking the double scale limit is really about where the D3 brane is placed in terms of radial coordinate, but that's not really the instability that we worry about. Okay. And this is a reasonable thing because even in the low energy supergravity, what you can confirm is that you compute the density of the energy sourced in the stored in G Raman fluxes, And then they basically scale like 1 over radius square. And what this means is that you can finally treat the Raman fluxes as a perturbation, even if the flux quantum is gigantic. And you can also do the similar exercises for H3 and the working. So,
Manki, can I just ask a quick question?
yes,
I was
yes.
going to ask about H3 because I was a little confused. Because H3 should not be a small perturbation on the Clavier CFT or the approximate Clavier CFT you're using. Are you treating it as small because of the gravity picture of the metric alone, or?
Oh, yeah. So I'm treating H as a small perturbation because in the near-to coordinate where the OPs of the fields are basically the unit diagonal, the vertex operator scale is like 1 over radius. And that this may not be quite surprising if you think about it. For example, let's consider WZW model. And then you take the flux quantum of H3 to infinity. Then what happens is the WZW model basically behave like large nonlinear sigma model with some flux where the you can treat the curvature and the flux as some small quantity in perturbation theory. So basically the same thing is happening.
Mm-hmm. Okay.
Yeah, but for some like order 1 flux quantum, you cannot really do this. But because the radius scale is so large, despite that the flux quantum is large, you can treat the vertex operator as some small perturbation.
Okay. Okay, thank you.
Sure. So we confirmed that in the KS solution, we can treat Raman fluxes as some perturbation. So what I'll do now is to solve the background solutions order by order in perturbation theory, where the perturbation theory is organized in terms of the radius, 1 over radius. There is one more parameter that I didn't really talk about, which basically measures the back reaction due to anti-D3. But I'll treat, for this talk, I'll just assume that this parameter is really small, and I'll solve the equations of motion in the probe approximation. But for the future work, I'm planning to also go to some high order in lambda and compute the back reactions as well. And what you can do, although I didn't really do it in this paper, is that once you found the background solution, then you can study the spectrum of the low-lying states in the open strings to detect the instability. I didn't do so because I obtained the leading order result in alpha prime, and that agrees with KPV, and we expect that we'll get the result that is in agreement with KPV. But for the computation, including high order alpha prime corrections, this is the thing that you need to do. Okay, so
Manki, just a general question. So what would be a spectrum of low-lying states that would indicate the instability? Like you're saying, like you could calculate that there's some tachyons, for instance. Is that what you mean?
Exactly. For example, in the story of KPV, what you expect is that when the instability happens, the some low-lying open string modes that describe how the D3 brains will puff up will have some negative mass or massless or unstable, for example, and all that thing is you can compute on shell.
Oh, you can compute on shell. So in principle, you could see it even from. Okay.
Yeah, because they are a spectrum, right?
Sure. Okay.
Yeah. So that is the thing that one can in principle do. So provided that you computed alpha prime fractions, that's something that you can do. Good. So let's first study the closed string background. So although for the actual computation, I needed some information about the third order solution in the closed string background equations of motion, let's just talk about up to the second order. The first order equation is basically given by this, where QB acting on the first order solution is 0. This basically means that the background solution that you turn on at the first order is marginal, which is reasonable. And this is the second order solution, second order equation, which is more non-trivial. To solve, although the second order equation is rather compact, as I told you a while ago, actually the string bracket contains infinitely many terms because it contains information about infinitely many fields. So you might worry that actually solving this is rather difficult. But there is a trick that you can use, which was developed by Ashok. What you can do is to split the second order equations of motion into the method part and into the messless part. The method part of the equation can be solved really easily because the BRST operator is reversible for the method states. For example, this is the solution. On the other hand, the messless part of the equation is not really trivial. After doing some CFT gymnastics, what you find is the following. First, you can write down the generic field at the second order, and basically it looks like the Einstein-Hilbert action, and the source term is exactly the one that you get by computing the 1 beta function. And once you have that, then you immediately realize that, okay, the solution to this equations of motion should basically agree with the warping or the Klebanov-Strassler solution to the second order in the radius approximation, in large radius approximation. So this is the solution that we find, and then we'll use this to study KPV. And I want to make a few comments. You can check that this background solution preserves 4 supercharges as expected from supergravity. And the space-time SUSY, that is preserved by the background will determine what is D-brane and what is anti-D-brane. And as I told you, we need some information about the third order solution, but I'm not going to explicitly solve it. I'm going to just assume the existence of the third order solution. And I think that is a reasonable thing because the Klebanov-Strassler solution exists to the fourth order in the large radius approximation. Now, the final step, we need to study the open string background because that will tell you the instability of the anti-D3 SUSY breaking. And as I told you, I'm going to put a stack of anti-D3 at the tip of the throat, and I'm going to solve the background solutions order by order in perturbation theory that describe the fuzzy sphere that is equivalent to NS5. So I need to turn on the first order background solution, and this is basically describing the positions of the anti-D3. And Fi will be a constant P by P matrix over the 1 radius. And then I'm going to turn on this first order background solution, and then I'm going to go to high orders in the large radius approximation, solve equations of motion order by order. Okay. So this is the first order equation for a string field, open string field. And as I told you, in string field theory, what happens is that equations of motion is only non-trivial in the massless part if you're solving the entire equations of motion at the same time. So I'm going to only focus on the massless part. This is the first order equations of motion, which is given by this equation. And then it is rather easy to show that the right-hand side or the source term vanishes. The reason is quite simple. We're putting anti-D3s in the background, and then psi 01c is basically the three-form fluxes, and then there is no coupling, three-form flux coupling in the anti-D3. So the right-hand side vanishes, and the left-hand side also vanishes because I started with the constant background solution. Now we need to solve the second order equations of motion, and those are the source terms that you can write. What you can easily find that as well is that all those source terms vanish. It shouldn't be very surprising because what I told you is that I'm putting the anti-D3 at the tip, and then most of the terms, like this term, and this term, describe the force as felt by the anti-D3 in the radial direction. And they should vanish because I'm putting the anti-D3 at the tip. And what this means is that I can also set the second order solution for open string to 0. Now this is getting a little more complicated. So I did the computations, and what you find is that most of the source terms do vanish again. And there is a good reason. For example, this term, again describe the radial force felt by the anti-D3, and they should vanish because I'm putting the anti-D3 at the tip. And those terms, you also know that you can easily check that those terms do not arise in Sugra, so it's reasonable. And then what those terms is that they basically look like these. So basically, they give you the equations of motion that describe the Myers effect. So the right-hand side, the source term is rather non-trivial, and then we have some left-hand side. And as you see, for this equation to admit a solution, the right-hand side must be BRST exact. The only way that the right-hand side or the source term is BRST exact is in fact by just canceling this coefficient. In the other way of saying is that the tuple is canceled. And so only when this condition is imposed, you can find a background solution to the third order. And if you remember, this basically agrees with KPV. The only difference is that now we're not in the KPV, as I told you in the discussion with Thomas. KPV used the SQL form of the anti-D3 action, but I'm not using that. So F3 is replaced with H, and Fi is related to the Sugra basis by some rescaling. But modulo those, we found a perfect agreement with KPV. And now let me conclude. What I want to tell you is that string field theory gives you a systematic framework to study random backgrounds. And to solve the equations of motion, I went to the third order in the equations of motion, which basically is equivalent to the fourth order in the potential. And I found a perfect agreement with KPV modulo some differences due to the SQL treatment. An obvious thing to do is to go to higher order in alpha prime and compute the open string spectrum. And if you have seen my paper, the computation is rather technical, and you don't really want to do it for high orders in alpha prime with pens and papers. But I really believe that it is possible to automate most of the calculations. So probably in the near future, we'll be able to do a more impressive computation. The other comment that I need to make is that it is quite possible that the expansion is asymptotic. So to a certain order in the alpha prime expansion, we'll get better and better approximation. And beyond that, our approximation will become bad. So I think it is also very important to understand when that really happens. I think for that, it might be really important to understand the asymptotic growth of the expansion. And I think there are many interesting things that one can do with this. So let's chat if you're interested.